my name is Chen Hao, and today I'll be talking about my project on topology and geometry of three-band models. So briefly speaking, I'm developing a mathematical tool which involves topology and geometry to understand uh, things like semiconductors and superconductors, which can be represented by the physics model of three-band models. So my research is in the field of topological physics, um, and topological physics is a field that is increasing in popularity in research lately, and its applications from quantum computing to string theory. So I'll first give a short introduction about what uh, something called Berry curvature is. So first of all, if you remember that the sphere is curved, right? Like the surface of the earth is a curved surface. So if we look at the earth from an external point of view, we can see that it's curved quite obviously. But the question to ask is, if we are on the surface of the sphere, how do we know that we are on a curved surface? Like if we're standing on the surface of the earth, how do we know that it's curved? Because from our perspective it looks flat. So the answer is that there's a mathematical procedure called parallel transport that can help us detect curvature on the space that we are in. So if you are on the surface of the sphere, you can parallel transport a vector in a loop, and when you go back to the original position, the vector will have rotated. So this is akin to holding an arrow on Earth and walking from the North Pole to the equator, to another point on the equator, and returning back to the North Pole. And when we return back, we will have seen our vector rotate, even though we have returned back to the original position. And mathematically, this is called holonomy of a connection, and this is studied in the field of differential geometry in math. So one question to ask is, if we can have curvature on like things like the surface of the sphere, can we have curvature of quantum states? So can quantum mechanics have a curvature of sorts? And the answer is yes. There's something called you can imbue a manifold structure on quantum states, and that gives rise to a notion of curvature on the space of quantum states. So for example, if we think of the space of spin half particles, which is like the electron, as the sphere, then when you parallel transport the electron in a loop on the sphere, and when you return back to the original position, you have some sort of rotation of the quantum state, similar to how our vector rotated. And this rotation is, instead of physically rotating the vector, it picks up a Berry phase. So this phase is a complex number which is of unit length. So you have a complex vector, right? And then when you parallel transport it one round, it picks up a phase vector. So yeah, so if you shrink this phase down to a very small loop, you can calculate a quantity called the Berry curvature. So how does Berry curvature have anything to do with solid state materials like semiconductors or superconductors? So the link is through Bloch's theorem. So if you have a real material like a lattice over here, if you have a lattice structure, lattice of ions, under quantum mechanics, it can be represented as a 3 by 3 matrix. So essentially, every material that you can think of can be represented by some matrix, and this matrix is called the Hamiltonian. So by solving for the eigenvectors of this matrix, we can get the quantum states. So the turns out that there's some topological aspects to the quantum states, and there's a topological invariant associated for each material called the Chern number. So the Chern number is sort of like an integer that labels each material that we have, and is a topological label. So yeah, and how do we calculate the Chern number for a material? We calculate it as the sum of the Berry curvature. So in essence, the Berry curvature of a material can tell us information about the topology, because if we sum up the Berry curvature, we get the topological invariant. So if you want to think of it geometrically, each material is like a unique map from the donut to the sphere. So if you think of the donut as a rubber sheet, you're sort of stretching the donut over the sphere, and there's a winding number of sorts because the donut has to wind over the sphere in some unique way, and this is where the topological aspect comes in. So so the Berry curvature is basically an important quantity that you associate with each model. So the Berry curvature in my research question is basically a 2D graph as seen over here on the right. So it's a 2D graph. Okay, so one question that I asked in my paper is, why do some 3x3 matrices have a Berry curvature that looks very nice, like it's very uniform and very flat? And this question is interesting because Berry curvature is responsible for physical properties like conductivity, and a more uniform Berry curvature leads to better behavior for the materials. So I seek out to answer why for some materials, for some 3x3 matrices, the Berry curvature is a nice graph. And I do so using the technique known as Majorana-Stellar representation. So there are other methods of understanding the Berry curvature, but this one, using the Majorana-Stellar representation, it has not been explored as much. So I used the MSR to write a mathematical formula, which you will see later. So what is the MSR? So the MSR is a way of decomposing higher spin states into multiple copies of spin half states. So what does that look like more simply? If we have a spin half particle like an electron, then you can describe the spin half particle as a vector of two complex numbers. So you can think of the spin half quantum state. You can write the spin half quantum state as a vector, just as a vector of two components, just that each component is a complex number. And in order to understand this complex two vector more simply, more geometrically, you can go through the Bloch representation to represent the spin half particle, the electron, as a point on the Bloch sphere. So essentially one electron can be thought of as a point on some sphere, and this is called the Bloch sphere. So one question we can ask is that if that kind of geometrical picture exists for two band models for spin half particles, then what is the use of it, right? So why is this Bloch representation useful? It's because if we calculate the Berry curvature for the electron, it turns out to be simply the solid angle or the area on this sphere. So you can see that it's a very nice geometrical understanding of the Berry curvature as simply the area on the sphere. So this is a very nice picture, and it leads physicists to understand two-band models very geometrically. So the question is, can we extend this to three-band models? So if we have a spin 1 particle, instead of having two complex numbers, now it's three complex numbers. So can we represent these three complex numbers as geometrically on some sort of mathematical object? The answer is yes. Through the MSR representation, we can represent the three complex numbers as 2 points on two spheres. So so that's the Majorana-Stellar representation. Then the next question to ask is, if we have a Berry curvature on the spin half particle being just a solid angle, being just the area on the sphere, can we have what is the geometrical picture for Berry curvature of spin 1 particles? And that's the question that I solved in my research. So um, so the key result in my research is I developed a new formula for Berry curvature of of the three complex numbers, the three complex vector, as in terms of the Majorana stars. So this formula on the top right here is the main result of my paper. So previously, physicists understood the Berry curvature of spin 1 states as the formula on the left, but this doesn't have this formula is easy to compute, but it doesn't have a nice geometrical picture to it. You don't understand it geometrically. So the formula that I developed is a sum of four terms over here, and this formula is beautiful because it can understand the Berry curvature. This formula for Berry curvature is written in terms of the two spheres. So what is nice about it is that the first term is the first sphere, the second term is the second sphere, and then the third and the fourth term is a mix between the two spheres. So in essence, I've developed this is the mathematical tool that I have developed to understand spin 1 quantum states geometrically. So this is the formula, and in order to and I proceeded to use this formula to plot to understand why the Berry curvature is relatively uniform, why the Berry curvature is so nice. So if we take this fifth graph over here, figure 12, and we split it up into the four terms over here, T1 to T4, then we get this graph, figures 8 to figure 11. So we can see that if our figure 12 is relatively nice, is relatively uniform, and if we split it up into figure 8 and to figure 11, then we see that there's some problems that appear here in figure 8 to 10. Namely, the figures 8 to 10 have these divergences. So these divergences are a curiosity, because if we have three divergent functions, right? Three divergent functions, which means that the function blows up to infinity at some point, and we take these three divergent functions and we add them up to get a non-divergent function, then that must mean that the coefficients of these divergences must be zero at some point. So that was the mathematical curiosity that arose out of my mathematical tool. So I spent the remaining of my time in the project to understand, to make sure to conduct a sanity check that these coefficients do in fact cancel. And after some mathematical procedure, I did show that the coefficients add up to zero. So that was just a sanity check on the mathematical tool that I developed. So for future work, since this is a tool, there's many aspects of this tool that I can further investigate into. And one interesting area to go into next, which I'm studying now, is abscissional points in these models. So what are abscissional points? If you are familiar with complex analysis, abscissional points are just the branch points of the square root function. So this gives rise to many interesting things we can investigate, like the Riemann surfaces of my model, and it could possibly lead to a topological characterization of solid state 3-band models in terms of Riemann surfaces, if we consider things like compactification of the Riemann surface. So this involves a lot more interesting math that I'm still studying and learning, and yeah, so this is the future direction for my research. So that I've come to the end of my presentation. Thank you. Thank you. Thank you. Okay, I met my mentor in the beginning of year 5. So towards I spent the around 3 quarters of the year developing this formula. I actually took a wrong turn by accident, and I had a formula with 8 terms, and none of and those were it's quite an ugly formula. But then after that I managed to simplify it down, and then I spent the remaining of my time studying these divergences. So as of now, I'm actually still continuing the project, and I'm in the phase of writing the paper. So I went on to investigate these abstraction points a bit further. So in terms of length, it's around the beginning of last year, so beginning of 2020 to currently I'm still writing the paper, but I hope to end the paper. I hope to finish this project by the end of this year, hopefully before my A levels. Yeah. Mm. Okay, this one. Mm. 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 That's the interesting thing. These spheres are actually, they must be indistinguishable, meaning that they must be indistinguishable, meaning that if I swap the two spheres, they, it should not matter. Like because up front. Mm. 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 Yes, yes, they can, because if we take the T1 is the first sphere and T2 is the second sphere, right? And then we add the two, we have T1 plus T2. So you see that the sum T1 plus T2, it stays the same if we exchange the first sphere and the second sphere, because we're adding them up anyway. Mm-hmm. Oh, no, no. Um, the Riemann surface, uh, the sphere is for the Madrona stellar representation. It's for the MSR. So the sphere is the sphere is the method which the sphere gives me this the two sphere picture gives me this formula, right? And then using this formula, I investigate a bunch of other things, and one of the things I can investigate is a term is it involves this Riemann surface. So this formula actually, the stars, right? Okay, if I go to this slide, the stars are actually calculated with as the solutions to this quadratic equation. So this quadratic equation, there's a square root term, right? Square root b squared minus 4ac. So under the square root term, if this b squared minus 4ac, because the b squared minus 4ac is a complex function, so if the b squared minus 4ac winds around the zero, around the origin, then we can get a, a branching behavior be, because of the square root function in the formula for the Madrona stars. So this Riemann surface is different from the two spheres picture. Yeah. And oh, yeah. Thank you. Sure, sure. Yes, here. Mm. Mm. Okay. Okay, so this better behavior, first of all, the these solid state models, which is like the semiconductor, so this lattices, right, in solid state physics, my mentor is using um, these solid state models as a analog. It's a analogous to the um, the fractional quantum Hall effect. So the study of this is called fractional Chern insulators. It's a study of how the insulators in solid state physics can, it's like is parallel to the fractional quantum Hall effect. So by studying these insulators, they are able to understand the quantum Hall effect better. It's like creating a one a analogous model. So um, my mentor said that the uniform Berry curvature, it leads to better behavior of the fractional quantum Hall effect in these insulators. Yeah. Mm. Yeah, correct. Better quantum Hall effect. Because because the Berry curvature plays the role of the magnetic field in the fractional quantum Hall effect. So with with the quantum Hall effect, you have the magnetic field and then you have the electron orbits. But for the insulator, you have the Berry curvature and then you have the electron orbits. So Berry, um, I don't think so. Yeah, it's just the Berry curvature that plays a role.